Hello friends. In my last session I told you the concept of superelevation or cant on a railway track when a train negotiates a horizontal curve. And there we derived the equation for the cant, and also we discussed about the limiting values of cant for different types of tracks: broad gauge, meter gauge and narrow gauge. I also told you in that session the concept of Cant deficiency. This session is in continuation of my earlier session. Now today we will discuss the concept of negative superelevation. And the concept of negative superelevation is important, particularly on diverting tracks. This could be like this, or when a turnout takes off from the tangent track, then how we design these tracks. Now in this case, let us say this is the main line and this is the branch line, and both are on curve in opposite direction. AB and CD are the rails for main line, and CB and let us say AE are the rails for the branch line. Requirement is that for main line this should be laid at higher elevation than this rail, and for branch line this should be laid at higher elevation than this line. That's a conflicting requirement. And similarly here, there is a tangent track, a turnout takes off, and therefore this point should be higher than this point. Now in this case, if you provide any cant for main line, that will be negative cant for the branch line. And these diverting tracks are designed taking into consideration the concept of cant deficiency. So what is done here? In this case, for example, in this case, if you do not provide any cant, because this tangent track doesn't require any cant, so if you do not provide any cant on the turnout also, then also you can maintain a speed requiring a cant deficiency, CD. But in the case of diverting tracks, what we do, first you calculate amount of cant required for branch line using this equation. E is equal to V square G upon 127 R. Let us say this is X. The speed on branch line is limited and you get a value of cant. Reduce this cant by an amount equal to cant deficiency. So actual cant provided on branch line will be X minus CD. And what is CD? 75 millimeter for broad gauge. And let us say this is actual cant provided here. Now generally this X is less than CD and therefore it is negative. So you provide a negative cant. What does it mean? This is higher than this rail. And then this becomes positive cant for the main line. So for main line, cant will be equal to CA. This is negative. So this becomes positive. Generally it is negative because X is small, CD is larger, and therefore this is negative. Now you add cant deficiency to this. So the total cant or theoretical cant on main line will be CA plus CD. And then using this equal to E, you calculate speed which is permissible on the main line. That is how we design the diverting tracks. Now let me take one example to illustrate this procedure. A 5-degree curve diverges from a 3-degree curve. 5-degree curve diverges from a 3-degree curve. So branch line is on 3 degree, branch line is on 5 degree and it is coming out from a 3 degree main line curve. 3 degree main line curve in reverse direction in a BG layout, broad gauge layout. The speed on branch line is restricted to 35 km per hour. What is the permissible speed on the main line? That is the question. So speed on branch line is given, so you calculate the super elevation on or Cant on branch line using this equation, V square G upon 127 R. So 35 square, G is a dynamic gauge, 1750 for broad gauge line, 127 into R, radius of the curve. And my last discussion I told you R is related to degree of the curve and R is 1750 upon D. D for branch line is 5 degree and therefore this is 175 into 5. This is equal to 48 millimeter. Now you reduce this by Cant deficiency and therefore the actual Cant to be provided on branch line is 48 minus 75, that is 27, minus 27 millimeter. Now this is the negative Cant. Negative Cant provided on branch line, but even after providing a negative Cant of 27 millimeter, you can maintain a speed of 35 km per hour without any risk of overturning or discomfort to passengers. Now for main line, the Cant provided is plus 27 millimeter. Negative Cant for branch line means positive Cant for main line. Add Cant deficiency to this. So this is 27 plus 75, that is 102 millimeter. This is theoretical Cant. Actual Cant is only 27 millimeter. But when you add Cant deficiency, it becomes theoretical Cant. So now you can calculate speed using this equation, V square G upon 127 R. Now R here is 1750 upon 3 because branch main line is on 3 degree curve. So that is 102 equal to V square into 1750 upon 127 into 1750 into 3, or V is 65.7 kilometer per hour. That is the speed which can be maintained on main line by providing a Cant of 27 millimeter. But when you design a horizontal curve, the speed, the permissible speed should not be more than the safe speed. Now, what is safe speed? Safe speed I will tell you a little later, but for the sake of completing this example, the safe speed is given by this equation. Safe speed is 0.27 square root of CA plus CD into R. CA actual Cant, CD Cant deficiency, R radius of the curve in meter, these are in millimeter, and this equation is taken from this equation only. When you put the value of G 1750 and E is kept CA plus CD, that is the equation. So if you calculate this, you will get the safe speed. CA is 27 plus 75 into 1750 by 3, and that will also be 65 kilometer per hour. It is 65 in this case because we have already considered the entire Cant deficiency here. So allowable speed on main line will be 65 km per hour by providing a positive cant of 27 on main line and a negative cant of minus 27 millimeter on branch line. That is how we design the diverting tracks. Now here I used this equation V safe. Now what is V safe? Safe speed on curves. Safe speed on curve is that speed where there is no danger of overturning of vehicle as well as no danger of derailment. That means the centrifugal force, the unbalanced component of centrifugal force and unbalanced component of centripetal force, they remain within permissible limit. Earlier, the Martin's equation were used on Indian Railways to calculate the safe speed on broad gauge line and meter gauge line. For broad gauge line, this is V safe is 3.65 square root of r minus 6 to 7. This is the equation to calculate safe speed on a horizontal curve of radius r when there are sufficient transitions provided. When there is no transition, then take 80% of this speed as safe speed. Similar equation is given for meter gauge line also and narrow gauge line also. But these equations are no more in use by Indian Railways. Rather, the safe speed on Indian Railways are now calculated based on theoretical consideration. And theoretical consideration is that if you are providing a cant of CA and there is a permissible cant deficiency of CD, then CA plus CD will decide the safe speed. So, for broad gauge line, this safe speed is 0.27 square root of CA plus CD into R. CA is actual cant provided in millimeter, CD permissible cant deficiency in millimeter, R radius of the curve in meter, and that is in kilometer per hour. And similarly, the safe speed on meter gauge line is 0.347 square root of CA plus CD into R. Again, CA and CD same, units in millimeter, R in meter. And for narrow gauge, still Martin's equation is good enough that it is 3.6 r minus 6, square root of r minus 6. That is the safe speed on narrow gauge, 3.65 square root of r minus 6. R is radius of the curve in meter. Now, these are the speeds where you provide full transitions on both sides of the horizontal curve. Now, what is transition? You can refer my next session on transition curve, but for the purpose of completion of this session, I'll just indicate here that when there is a tangent track and there is a circular curve. To join this tangent track with the circular curve, because it's a straight line, this is a circular curve of radius r, we provide a transition between these two so that there is a smooth entry from tangent to the circular arc. This is called the transition curve. In case of a non-transition curve, when it is not possible to provide transition curve because of site restriction, then the concept of virtual transition is adopted. When you do not provide any transition between the tangent track and the circular track, then as soon as this vehicle enters the circular curve, the centrifugal force or the cant will be introduced suddenly. Now, when a vehicle is moving, when the train is moving on a tangent track, it is the linear velocity. When it enters the circular curve, it becomes angular velocity. So angular velocity, when the first bogie reaches this point, tangent point, that is the start of the angular velocity, and the train will attain the complete angular velocity when the rear bogie of the train reaches this point. So in case of a virtual transition, it is assumed that when the bogie is in this position, that half of the length of the bogie is on the tangent and half on the circular curve. In that small length of the transition, the Cant deficiency is achieved. And this length or center to center between the bogies, this distance is 14.6 meter for broad gauge, 13.7 meter for meter gauge, and 10.3 meter for narrow gauge. Now this is the criteria that the Cant deficiency should be obtained or should be attained within a virtual transition of center to center distance between two bogies, and that is these distances, 14.6 meter. So what Indian Railway standards suggest that this Cant gradient on this virtual transition should not be steeper than 1 in 360 on broad gauge line and 1 in 720 on meter gauge and narrow gauge line. That is how we decide the safe speed on the horizontal curve where there is no transition. So in fact there are 4 cases which can be encountered in the field. One, when you have fully transitioned curve, then safe speed is given by these equations. These are from theoretical consideration. When you do not have any transition, non-transitioned horizontal curve, then in that case the virtual transition. The third case could be when you have a horizontal curve without Cant. Curve without Cant. Now, when the horizontal curve is very flat, radius is very large, then you don't need any kind of Cant. And in that case, you do not need transition also. So the criteria in that case is the same, that the Cant gradient should be limited to 35 millimeter per second in case of broad gauge line and 55 millimeter per second in case of meter gauge line. So it is only the Cant deficiency which is basically coming into picture, not actual Cant, because there is no Cant provided. The fourth case could be when you have inadequate transition. Means there is transition length, but that is not sufficient. So here it is fully transitioned, no transition, without transition and without Cant, and with inadequate transition. So transition length is limited. In this case, what is basically attempted, that this is the circular curve, this is the transition curve. The rate of change of Cant deficiency should be such that the overall speed on transition and circular curve is optimized. Means it is almost uniform when it takes off from the tangent till it reaches the circular curve. This speed, average speed on the transition, average speed on the circular curve is almost same. And for that reason, these values are again used. That rate of change of Cant deficiency, 35 millimeter per second on broad gauge line and 55 millimeter per second on narrow gauge line, meter gauge and narrow gauge line. So that is how these 4 cases are dealt in the field. Let me explain this. How do we determine the maximum permissible speed on a track with the help of one example. Calculate the superelevation and maximum permissible speed for a 2-degree broad gauge transition curve on a high speed route with maximum sanctioned speed of 110 km per hour. The speed for calculating the equilibrium superelevation is 80 km per hour as decided by the chief engineer, and the booked speed for goods train is 50 km per hour. Now here in this question, the speed is restricted to 80 km per hour on a broad gauge high speed track. So the first is that a 2-degree curve will have a radius of 875 meter. Calculate what is the requirement of Cant for a speed of 80 km per hour. That is the speed suggested by chief engineer. So E is equal to V square G on 127 R. Dynamic gauge, broad gauge 1750 into 80 square upon 127 into 875, and this is 100.8 millimeter. Now this is less than Emax, and therefore it is okay. Now you calculate what is the requirement of the Cant for the maximum sanctioned speed, and therefore it will be 1750 into 110 square into 875. This is 190.6 millimeter. Now actual Cant which is to be provided is 100.8 millimeter, but if you want to run the train at the maximum sanctioned speed of 110 km per hour, that will require a Cant of 190.6 millimeter, and therefore the Cant deficiency here is 190.6 minus 100.8, that is 89.2 millimeter. Now this is more than your normally permissible limit of Cant deficiency, 75 millimeter. But when you are putting this kind of restrictions on speed, that the curve to be designed for 80 km per hour, then in that case this can go up to 100 millimeter. And because it is less than 100 millimeter, so design is fine. Okay, that means, what does it mean? That even if you provide the Cant of 100.8 millimeter, it is possible to run the train at a speed of 110 km per hour with a Cant deficiency of 89.2 millimeter. Now, third is here the goods train. Goods train should also run on this track without any discomfort. So E for goods train, or you can say slow train, is 1750 into 50 upon 127 into 875. Booked speed for goods train is 50 km per hour, and this value is 39.4 millimeter. Now actual Cant provided is 100.8. Cant required for running a train at 50 km per hour 39.4. So what is the Cant axis? Cant axis is 100.8 minus 39.4, that is 61.4 millimeter. Now this is less than permissible Cant axis on a broad gauge line. So it is less than 75 millimeter, and therefore okay. Now all three are satisfied with Actual Cant provided is 100.8 millimeter. What is the safe speed? Safe speed will be calculated by this equation. 0.27 square root of CA plus CD into R. CA is 100.8, CD is 89.2, right? And R is 875. So when you put these values, you will get same speed as 110 km per hour. That is 100.8 plus 89.2 multiplied by 875, and that is 110 km per hour. Because I told you this equation is derived from this equation only. So if you are putting E is equal to CA plus CD, you should get the same value of E. This can be lower than 110 if this exceeds 100 millimeter. In that case, Cant deficiency will be limited to 100 millimeter. Accordingly, this speed will be adjusted. It should be compared with maximum sanctioned speed. It cannot be more than, the maximum permissible speed cannot be more than sanctioned speed. Sanctioned speed is basically for which the track has been designed. So lower of these two values should be the allowable speed or safe speed on the curve. That is how we design the horizontal curve. So friends, thank you very much for watching this video. In the next session, we will discuss the transition curve.